So welcome to the XSEDE MPI workshop. I'm John Urbanek, coming to you from Pittsburgh Supercomputing Center. This is the workshop that most excites me as a parallel programmer, because this is the most powerful of all the parallel programming techniques. I think we have a quorum, so we can go ahead and get started here, because we do have a lot to cover this morning. This morning's lecture is kind of fun because I get to expose to you all of the fantastic expanded capabilities of MPI that exist mostly to make your life easier. With what you've learned just yesterday, you could pretty much write any application. You can really put together, any kind of algorithm with just those capabilities. But you're going to see how many powerful features MPI has, just to relieve you of a lot of the bookkeeping and details as applications grow larger. And so we're going to cover essentially the entire MPI API. We'll cover almost all of the routines that exist, even though I said there are upwards of 400 MPI routines, and you only know at this point in time 15 or so of them. We're going to cover a lot of ground fast because they live in families. They group together. They have a lot of themes. And so by the time we're done here, you will know what most of those 400 routines do, and you'll know where to find them when the time comes, even if you won't have memorized the list certainly. So let's get going. I'll give you a little bit of an overview before we do, though, in that the MPI API has expanded and evolved over the years. And because it is a very good standard, I think I emphasized that yesterday, and I'm happy to reemphasize it here, because the Standards Committee has done such an admirable job of being realistic and pragmatic, so they don't implement things that can't be widely portable and implemented quickly. The standard has really been coherent and cohesive over the years. And it's really not important to know any of this stuff. It's not really important to know which ones were originally in the 1.1 specification, which became widely used, and which ones were introduced later, because they all fit together pretty seamlessly. So you, as somebody coming into MPI these days, you don't need to understand any historical perspective. You don't need to worry about versions. You don't have to worry about, am I using version 3 point whatever. That's what you will find everywhere these days. Okay, so let's jump right in to some of these more advanced capabilities. One of the very useful ones that you'll find yourself coming across either in existing MPI codes or wanting to take advantage of yourself are user-defined data types. So far, everything we've done has involved one of the predefined data types, like MPI init or MPI float. And while those are certainly very powerful and useful and widely used, you will find yourself wanting to use the built-in data types, because the messages that you'll be sending in your real applications will be collections of data types. You'll be sending a message in our weather example, for example, that we used yesterday, and we'll use again today. If we're sending weather from one state boundary to the next, that array of weather might include a bunch of floats to represent some of the temperatures, some other floats to represent the pressures, and some other floats for humidities, and they might have different array sizes. You want to send them as one cohesive message. You can do that. You can put the data together in one cohesive message. But I'll give you plenty of examples as we step through this. You'll see how well motivated it is. And even our Laplace code will be a great example of where you would want to use user-defined messages. So that's kind of the second bullet up here, non-contiguous messages. That's a fancy way of saying a bunch of different data types that we want to combine into a single message for logical reasons. This first bullet point's kind of obsolete these days. There was a time when people would assemble clusters from a lot of different machines, and sometimes those different machines would actually have different formats. Big endian versus little endian. That's a computer science way of saying that sometimes the most significant bits are the first one or it's the last one. These days, formats have converged so much on kind of Intel-looking architectures, or even if you're using ARM architecture, it's the same kind of IEEE formats, that's not so important. But in the event that you did have to do data conversion as you send data from one type of computer to another, MPI will take care of it automatically. Not so much of an issue these days. What is an issue is making these non-contiguous data types, creating your own data types from your own data structures that apply to your applications. And it's very easy to do that in MPI. It's basically a two-step process. The important and interesting step being where you define for MPI what the data type, the new data type that you want to use is. And you define that with a selection of routines that are available. I'll step through the most important ones here, example by example. You do that by basically building up your own data type from existing data types. So you might say we have a bunch of a big strip of floats like we have in our Laplace code. We can make that into a new data type. Or you could have much more complex things, like you could have something that's a a bona fide C structure or Fortran object. It's got a lot of different pieces to it with different types, and you can turn that into a single message. We'll step through these examples. So after you do that, after you define this for MPI, and you can build this up in a hierarchical fashion as complicated as you'd like. Many times it won't be complicated, though. It'll be very straightforward. It will simply be a section of an array is all you want to send. So after you define those, then you commit those. Once you commit it, now it's a type, and it's as good as any of the built-in types to use in any of the MPI calls. So we'll start out with one here that very much familiar to us as we're thinking about our Laplace problem, which is the vector type. And the vector type, as the name implies, is a type that basically gives you a sequence of the same data type that you're going to use over and over again, either a row or column of data, typically in, say, a 2D array, going back to our Laplace code. With our Laplace code yesterday, we saw this is one very logical domain decomposition we could use for the metal plate. We chose to use strips, one-dimensional strips, but if you wanted to use these subsquares, for example, it's very straightforward. It's not straightforward unless you have these MPI user-defined types, though, because as you know, for example, in C, we know we can send data as these rows because it's contiguous data. But if we try to send a column in C, how would we do that in the array? Because the data in the array isn't contiguous. The array in C is defined so that the values go across the array in these kind of rows, these raster scanned rows. And that works great for sending a strip of data like this, but how will we send a column? Well, the answer is a user-defined data type. We can define a column simply by letting MPI know that a column has a certain number of elements, but also a certain stride. So the stride argument is the magic in defining a vector type. The stride says how many to skip between each element. So if we have a 1,000 by 1,000 array, we tell it take the first one and then skip 1,000 elements and take the next one and then skip 1,000 elements. So a stride is a nice way in an array to be able to define a column or even a diagonal. You could say skip 1,001 and you could create a diagonal. And in 3 dimensions, you could tell it to skip. We'll go on to a 3-dimensional example on the next slide, but in 3 dimensions, you would tell it to skip 1,000 times 1,000 or to skip 1,000,000 elements and you jump down to the next one. So it is a very simple idea, a stride, but a very powerful one. And again, it also applies to many other areas of programming when you're dealing with arrays and you care about performance or the way things are laid out. But at any rate, the vector type allows us to define for ourselves both a row, which isn't a big deal in our C version, but here it'll be convenient too. Once we define a row, then MPI will think of it as one single message, and we can define a column, which will also be thought of as one single message. So once we commit those, then whenever we go to send or receive a message, here's our MPI data type, is row, this new one that we've defined. So we can send a row or a column, and we're just sending one row or one column, and will be this entire message. So you can see it's convenient. It's logical. It saves us from having to bundle up a message. It makes our code a lot cleaner for the entire rest of our code. Once we've got this thing defined, we can use this thing freely. And so it is the way I would do the Laplace code, certainly. Now in 3 dimensions, which we'll talk a little bit more about going to Laplace code in particular in 3 dimensions in our Laplace code review this afternoon. But I think even prior to that, I think the notion of going our Laplace code in 3 dimensions is pretty intuitive. It's a pretty obvious idea that if we would expand our Laplace code from a square metal plate to a big cube, our domain decomposition would be a bunch of smaller cubes. So this might be one of the smaller cubes that we would break our big cube of our Laplace cube problem into. And this is typical for most real scientific problems, which are, of course, 3-dimensional. Question? No. Oh. So we have a real 3-dimensional problems. We break up into 3-dimensional chunks, and we use this same halo technique that we've gotten, we're starting to get involved with our Laplace code. But the halo zones in a 3-dimensional problem are actually going to be a surface of a cube, right? The cubes are communicating surfaces to each other. So if this is one of our subcubes right here, you can imagine you want to send this whole face to your neighbor and receive data, this face from your neighbor, in which case these user-defined data types are, once again, come to the rescue. So to send this whole face, let's say this is our 3-dimensional cube here, and to send, let's say that this is the first, in the way that this cube is oriented, that the array is stepped through like this. This is the first element, this is the next one in memory, and it scans across the rows like this. So this is the order of our array. Then to send this first face, we could just stick it, point it to the first element, and then send the next 49 elements because they're contiguous if we wanted to, because this is 7 by 7. So we could send the whole face. And then to send this face, we could point it to this first element here and tell it skip 7 and go to here. So we could send 49 elements with a stride of 7, and it would send this blue face. And then to send this red face upwards, we could say start here and then skip 49 elements, and then you're going to be on this one. And it would go through this entire face. And we'd send 49 elements with a stride of 49. So I hope you can see it's very simple using strides to be able to send different planes in different directions of an array. And so that's where we could use vector type to do that. Now, in reality, Halo codes, as you recall, no doubt, since you're thinking heavily about this right now, I hope, have actual ghost zones on them. You don't want to send the whole face. You actually, if you start talking about the ghost zones here, if we had this face, we really only want to send the interface here. Just like on the Laplace code, when you're sending strips, you don't want to send the entire strip. You really want to send 1,000 elements. You don't want to send 1,002 of them. You don't want to send the 2 pieces on the end that are the boundary conditions. And likewise, if you're sending faces in 3 dimensions, we really only want to send this inside here 5 by 5 face. And so if you don't get that, think about, again, ghost zones that you want to have to send messages and receive message buffers into. And so if you really had in memory a 7 by 7 cube, you really only want to send the 5 by 5 piece that you're responsible for on the inside, and the outer layers are your ghost zones. Well, now, how do we send a message that is 5 by 5 block on the inside? Once again, the user-defined data type, we could define a vector that's 5 elements long here, but still has a stride of 7, and so it would send these 5, and then it would skip. It would know that the blocks are really 7 apart, and it would skip down to here, and then we could send these 5. We'd skip down to here and send these 5. So we can send an inside face. So you can do that with vector data types. And you can also use the create subarray type. So from the previous slide, you'll see that that was one of the routines. And in this case, that's what I would use. It's the most elegant. If you look at subarray allows you to point to the beginning and end of the array and to define the dimensions you're working in, 3 dimensions and the sizes, and it'll do the math for you. It'll figure out the strides for you. So you could use either one of these, but I think the subarray type is really useful when you get into these kind of situations here. So once you define a subarray, then for the entire rest of your code, whenever it's time to send one of the faces of these cubes, even though it's this inside face and it's got a little bit of math to it and some indices, it's boom, it's predefined for you. So a nice walkthrough of the 3-dimensional example is on this Stack Overflow page if you want to see what I just basically stepped through, but that would be the generalization of the Laplace code. So I've spent a lot of time on this particular case because this Halo technique is extremely general and it works with many, many problems, and you're going to come across this when you're working with 3-dimensional real-world problems continuously. So this is worth a few extra words here. Okay, and let's see, no pending questions regarding this stuff. Okay, well, there are certainly many other codes that you could create that aren't just Halo zones. For example, you might have a molecular dynamics code. It's a very popular application where you're trying to model molecules moving around in 3 dimensions. And your domain decomposition for a molecular dynamics code might be to take your original space and break it up into smaller boxes. So if we had a 2-dimensional molecular dynamics code, we might break our space up into these 9 smaller boxes here, and our molecules bounce around, then each PE is only responsible for 1/9 of space, and so things are going to scale up and run a lot faster. But in this case here, our messages are going to be not a face of an array as much as they're going to be the actual molecules themselves that are migrating. In this particular case, and point in time right here, the molecules right here are moving to the left. So in our next time step, these molecules, 3 of them here, are going to move from this PE to this PE. And so we want to make sure that we capture that migration with a message that includes those 3 molecules. Well, we can define a data type to do that very easily. The index data type allows us to create a message that's a pointer into an indexed array in memory. So if we have a particle list in memory, that's all the particles in this PE. So it has a particle list that's 6 things long, and it's got 6 molecules. We can say, send the message that corresponds to the data from positions 1, 5, and 6 in this array. If that happens to be these 3 molecules, send that as a single message over to here. And so that's a nice, convenient, elegant way to package that stuff up into a message. Now that you might right away think, but wait, isn't that message only valid for that one time step? Are we creating a message type that's only going to be used once essentially by this one PE? And the answer is that's exactly what we're doing. And the reason that you might want to do this instead of packing up and sending 3 little individual molecules yourself is that, first of all, it can make your code very clean and make it easier to read. You know, here's a single message that we're going to send and receive that has all the molecules, but it's also very efficient. That might surprise you that it's more efficient for MPI to create an entire data type to be used once to send 3 molecules than it would be for you to go and grab from memory yourself these 3 separate items and create a loop with 3 separate messages and just send 3 separate individual molecules as 3 separate messages. But in reality, MPI is constructed and tuned to be incredibly efficient at exactly this kind of operation because it is so important and so common. So MPI is better at going and fetching things from memory and sending them than you are yourself. Why is that? Well, behind the scenes, for example, MPI in this case might go and just point the network interface. In reality, the hardware to send and receive messages over the network goes through a network interface. Network interface cards today are very smart, and they can go find stuff in memory themselves and do it directly and save you doing save any copies being made, which is expensive. And so NPI, when it sees something like this, is so smart, it will go and it won't bother copying anything. It'll just send the right data to the network interface card. The network interface card can go to memory, fetch things itself, send it over the network, and it all happens as efficiently as it can possibly be done. And so that is why that might be the most important reason to use a message that's only created and used once. And so that's very surprising to a lot of people. At first, they think, you know, these user-defined message types are great, but I only use them when I've got a message that I'm worth defining and using for the entire code. No, these throwaway single-use examples are very efficient as well. Now, an important thing to note is that when you're creating a message that's only going to be used once, this little step down below here that I haven't emphasized so far, which is to free a message type, becomes important. If you create a message type and you're using it for the entire code, like our rows and columns here, you should also free it at some point when you're done with the code. But if you don't, it's not the end of the world, because who cares? When the code ends, it's going to go away. But if you're creating a message type dynamically as you go over and over, and you want to make sure that you delete it as soon as you're done with it. So make sure you do free these so they don't pile up and you run out of memory with all the user-defined message types that are being committed. So you can create a message, use it for a single step, and throw it away. And that's a very valid use for this kind of capability. When you go to receive a message like that, when you receive it into a buffer, it's going to be received as a bunch of individual particles because the number could vary from one step to the next. It typically will, right? In this case, we're sending 3 molecules across here, but the next time we might be sending no molecules, or we might be sending 1 molecule. And so the message size that's coming in here is going to vary. So you can receive it, and one approach you can take is you can say, I have a worst case scenario. I have the maximum number of incoming molecules that can be received. And so you can stick in this maximum buffer size, and it'll allocate a buffer, and it'll be able to receive up to this many particles. And then after the message is received, you can get the count. You recall when you receive messages, we have this little status parameter on the end. We didn't really use it so far. Well, now you can see one of the uses for it is after you receive a message, after the fact, you can use it to see, one of the things you can do is see how many particles you had. You can also use it to see where a message came from or what its tag is if you didn't happen to filter on those. But in this case, we're going to use it to see how many particles we actually received. And so with our previous message, we would have 3 particles come in. Our worst case, we might say you can receive as many as 100 particles. And so it'll put a buffer for 100 particles. It'll know that it received 3 after you get the count. And now you know how many particles you've got to deal with. Now, that might disturb you a little bit. You might say, I don't really know what the maximum number is. Maybe the worst case of a real molecular dynamics problem, you might have many millions of molecules, and I can't set aside a buffer for the worst case. That's just, I'm not comfortable with that kind of thinking. And that's fine too. You can also, in MPI, look dynamically before you even receive the message, before you even do a receive, you can see how big it is, and then dynamically allocate memory. And in a lot of scientific applications, that's exactly what you do. Dynamic memory allocation, just creating buffers as you use them because things change in size and are not predictable, is a very important technique, just in regular serial codes. And MPI supports that very well. In this case, here's how we do it. We can probe a message. This means you're looking for a message that with the right source and the right tag, but you're not going to actually receive it. So it's still sitting in that receive buffer somewhere. You haven't pulled it into your memory yet, but you can see things about it. In particular, you can see its size. So we can look at that message. We can say, hey, it's 3 particles. And now we can allocate a buffer. This happens to be C memory allocation, but the similar thing in Fortran. we can allocate a buffer that's exactly 3 molecules in size. So we're never going a worst case. We're not worrying about that. We're just going to allocate exactly the right size buffer. Now, one of the neat things that MPI will do is also worry about how many bytes should you actually allocate to that message, because you don't want to worry about that math. How many bytes or message might be complicated. For a molecule, it might have a bunch of different floats in it for velocities. It might have some integers in it for different types, species of atoms that make up that molecule. And so you don't want to have to worry about doing that math. MPI will do it for you since it's platform specific. So you can, after you get the count, you can get the size or the extent of the message, and then you can use that to determine how many bytes to allocate in your buffer. And now when it's time to receive it, you're receiving exactly 3 molecules into memory. And so you can go either way. If you have some worst case scenario, you can keep it simple. But if you really want to keep things dynamically allocated, because things are very mutable in your code and you don't want to worry about what's the worst case, I just want to deal with this particular case, you can do that. So this is a very, very common case in real large codes. Okay, questions. How about if you actually want to send stuff from that's scattered around memory itself? It's not just in a nice array, but it's scattered all over memory in different places because you've got something like a linked list. A real linked list is where you've got one thing in memory pointed to another thing in memory, pointed to another thing in memory, and you've created that somewhere off in your code, usually a bunch of dynamic memory allocations. And a linked list is a very common type of structure to have, and there are more complicated structures you can create with pointers. And if you've got those, how do you deal with that? Well, instead of having a regular index type that points into an array in memory, you can have an index type that has a bunch of memory pointers that says where everything's located in memory. Very straightforward to do. It's the H index type. And when you do that, you should note that MPI has a special data type used for memory pointers. It's called aint. So this is address int, I think it stands for. And you can create an array of these memory pointers. And you can go ahead and add things into this array right here. So we have a while loop that's going through some linked list, for example. And whenever it says something in this, finds something in a list it wants to send, it can get the address of that item and stick it in this buffer. And now when we're done and we've accumulated all of our stuff scattered throughout memory, wherever it is, we can create a type that will point to all those things in memory, and we can send that item. The data type will be something that points from the data, excuse me, the pointer to that data will be the MPI bottom. That's basically saying the bottom of memory. So that's just saying, hey, we're using memory pointers here. Things are all over the place. There's no particular location. So we have the MPI bottom is the bottom of memory, and we're going to send one of this user-defined data type, this items message type that we've created here. And then we can send that off as a single message. And once again, MPI will make sure that in the most efficient fashion possible, it goes and collects all that data scattered through memory and sends it on its way. And once again, this is a data type that you're going to use and throw away once, so you want to make sure you free it when you're done with it as well. We can hand pack a bunch of things into our single message if we want. If we want to, go through and just stick a bunch of grab things from an array in whatever pattern we want. We don't like to use the predefined index type, or for whatever reason, we can feel free to do that. So you can go and create a message, and you can pack a bunch of this item into it and send it on its way as a packed MPI packed data type. So this is one that MPI has predefined for you. You pack a bunch of stuff into it, and then on the other side, you can receive it as a bunch of those items. And once again, it's going to vary maybe from one time step to the next, so you can see how many of those items there are, and then you can unpack them. And the nice thing is when you use the pack and unpack routines, MPI will keep track with this position pointer of where you are in the packing and unpacking of these items. So it knows where to pack them in as you're adding them. And when you unpack them, it'll go through and keep track of it. So you can unpack them all and get them. You can also, if you happen to know that if you want to receive them all at once, you can get the count of them and just receive the whole packed buffer. Now, if you start talking about packing individual items, you might find yourself wanting the real ultimate flexibility, which is to pack a bunch of different type items. Very much like packing in a C data structure or a Fortran object, where each item that makes it up is totally different type. So here's a C data structure. We've got an integer, we've got a character string, got a double, another integer, and we want to send this as a single message. And that's a common enough thing to want to do. MPI makes it very easy to do that. We can go ahead and pack in all the different data types we have right here and send that as a packed message as well. But we have to remember to unpack this in the right order. So on the other side of this, we can unpack this in the right order. Now, one of the things that you really need to pay attention to when you are dealing with structs in C, well, maybe you don't have to pay attention to it. You can ignore this a lot of times as a serial programmer, although you should be aware of it. But now we've got to be aware of it, is that in modern computer architectures, almost any processor you're going to come across, when you're actually dealing with a structure in memory, modern processors like to have things lined up on certain byte boundaries. They don't like to treat every single byte in memory, byte 0, 1, 2, 3 is equal. Instead, they like to grab things in chunks. And so a lot of processors will insist that things actually line up on, say, 4-byte boundaries. So in other words, if we look at the structure here in memory, and we know that a character really only takes up a byte, and an integer takes up 4 bytes, and a double takes up 8 bytes, we might say this is 13 bytes for the structure. But if you actually go and look at the size of it in memory, just as a serial programmer, you might find that it actually takes up, say, 16 bytes, because for whatever reason, you'll see the compiler is allocating 4 bytes to this character. It's adding in 3 extra pad bytes. This is one example here. This varies by platform and compiler, so this is why it's platform specific, but most compilers will pad this stuff out to keep the hardware happy. And so even though this thing nominally takes 13 bytes, in reality, you'll find it takes 16 bytes. And so that's just an issue, again, as a serial programmer, you should probably kind of be cognizant of. However, in MPI, we can make this go, we can deal with it in a very portable way, because MPI will find out the extent of our data types for us. And so as we pack these things into messages, it will make sure that things get properly packed and properly unpacked and repadded in their destination. So if you deal with actual structures like this and you want to send and receive these as messages, you need to go through a few steps here to make sure MPI packs things correctly with the exact right size, and it will send them along and it will unpack them and keep track of all the padding. So a little detail you have to worry about if you want to use structures, but a lot of times the structure is the natural thing to use because your data type is made up of a bunch of mixed different things. Okay, let's see, somebody comments here, one comment about the dynamic approach. You should not forget to deallocate memory. Yes, when you're allocating memory in C, you should be deallocating it as well. So if you're dynamically allocating buffers, you want to deallocate them as well. Although, because memory allocations can be very expensive in C, a lot of times people will allocate a buffer and then not deallocate. We'll try to reuse it if it's smaller. So you'll find a lot of logic like that. You won't free and allocate a buffer for every send and receive because it's too expensive. So you'll only deallocate it or reallocate it if you have to. You'll allocate one that's conservative, intermediate size, and so these are lots of little optimizations, but they're standard things if you deal with dynamically allocated memory a whole lot. Okay, as I've hopefully pointed out enough here, the notion that you should dynamically create a data type just for a single message, again, seems wildly luxurious at first, but extravagant, but it actually makes perfect sense for performance reasons. So don't hesitate to do that because MPI will do a better job at gathering the data than you. Okay, that's enough about the user-defined data types. I hope you can see how both efficient and useful they are. They can make your code a lot cleaner and easier to write, and they can also make things run better. Let's move on to the other, another big topic, one that you will certainly find useful if you do any kind of MPI coding, and that's collective communications. Something we've already talked about with broadcast and reduce operations. And these are anytime you've got an operation that all the PEs have to participate in, that's a collective routine. So we saw that with broadcast, all the PEs participate in broadcast. With reduce, all of them do. With barrier as well. So the class of collective communications is pretty large because there are lots of useful things that are collective operations. One of the more useful ones is the scatter operation. It's not unusual in your algorithm to find yourself wanting to send a bunch of data and distribute it out to different PEs, not broadcast it, because we don't want to send all the data to all the PEs. Instead, we want to send a slice to each one of the PEs in an organized fashion. So for example, PE0 might have this array in memory, and it might like for each one of the PEs to get one element of that array, and this is a scatter operation. So with a scatter operation, you point it to the beginning of the array and you say how many you want to send of each type, because it doesn't have to just be one of each type. It could be multiple ones of each type. And you go ahead and send things out with a scatter operation. And then in one fell swoop, one call that they all participate in, all the PEs will end up with their subchunk of the array. And again, this is a very, very common thing to find yourself wanting to do. The inverse of scatter, which is also quite common, is gather. Gather is where you've got a bunch of data distributed on different PEs, and you like to gather them back into one central place. And so very often PE0. Doesn't have to be PE0 for these cases, by the way. You'll notice the collectives always have a root argument, and very often it'll be PE0 because that's very often the manager PE, but it's up to you to define it. So you might have a lot of data scattered around. You'd like to gather it all into one place, and that's what the gather operation does. And again, it's a very common type of thing to find yourself wanting to do once you start writing algorithms. There are a lot of variations of this. There are the V or vector versions of these operations, which allow you to vary the count for each PE. So you don't have to send 1 to every PE or 2 to every PE. You could send 1 element to the first PE and none to the second, and then 4 to the third. And that's the reason these things are called vector versions, because that means in addition, the arguments that you supply to these commands, in addition to the regular ones, you need to give it a vector or an array of counts for each one of the elements. So they have an additional argument in there, which says how many to send to each one of the PEs that are out there. But again, this is not an uncommon thing to use. And a lot of times you'd also like all of the PEs to end up with that result. So you might gather all the data together on the PE0, and that collected data might be useful for all the PEs to know. And so you could do a broadcast right after that. So we could do a gather and then gather all the data in one place and then say, okay, it's all collected together. Let's broadcast it back to all the PEs so they all have a copy of this collected data. Well, that's such a common thing to do that instead there's an all gather that does that in one step. And it is not only more convenient for you as a programmer, but it also is more efficient too, because the network can do usually smarter things than actually gathering it all and then broadcasting it. It can kind of collect it and so that it all ends up in the right place at the end in a more efficient fashion. But at any rate, from the programmer's perspective, this is the equivalent of doing a gather and then a broadcast. And there are all versions of lots of routines in MPI. So whenever you see the all, that's what it means, is that the data is going to end up back on all the PEs. You don't have to add in your own reduce. And so reduce operations, speaking of those, have some other advanced capabilities. You can use reduce not just to reduce down to a single value like we did with our pi example, where we gathered all the data with a sum, but you can do that for entire arrays, element by element. And so you can take it, if we have all the PEs have an array of 10 elements, we can do a reduce on all those arrays, and then you'll end up with an array of 10 elements with the maximum in this case from in each one of those slots from each of the arrays. You can also define your own reduce operations. There are a bunch of predefined ones in MPI. As I said, the ones you're very likely to find yourself using at some point are sum and minimum and maximum, but there are also a handful of other predefined ones, and you can even create your own if you find it necessary. And for min and max, you might find it important not just to have the minimum or maximum, but find out where they're actually located, and you can do that as well. There is all reduce, which means you do a reduce to get the value, and then you might want all the PEs to know about that value, and so you might do a broadcast. Well, you can do that in one fell swoop as well. So whenever you see that all operation in MPI, it means it's equivalent of doing kind of the reduce, but then doing a broadcast afterwards. And you can do, I won't spend a lot of time on some of these less useful, more esoteric ones, just make you aware of it. You can also reduce data just locally. Don't even do it through MPI just to get the maximum value locally. There are a lot of operations, but you're less likely to use these, so I won't go through them all. But the collective operations in general bring us to the next topic, which is communicators, because anytime you do a collective operation, you'll notice that one of the arguments to it is a communicator. And so far, communicators have just been this MPI COM world. But I already mentioned to you yesterday that communicators can be used to break up PEs into various subsets, so that if we had our weather model, we might have the ocean PEs and the land PEs as different groups doing different things. And so that's very important capability to have, to be able to break things into different pieces, because if they go off in their own ways in the code and you want to do a collective operation, like let's say a barrier, it's the easiest one maybe to illustrate this with. If they go off, if the ocean PEs go off to do some kind of mathematical operations and the land PEs go off to do some other operations, what if the ocean PEs want to do a barrier as part of what they're doing? Well, if they try to do a barrier, the other PEs over here that are working on the land stuff aren't going to be in any position to participate in that barrier. So we'd have a problem if we only had the world communicator, because we can never call a barrier or any collective operation for that matter, because all the PEs need to participate in a collective operation. So if the ocean PEs want to do a barrier and over here the land PEs want to do, say, a broadcast just amongst the land PEs, they'd have a problem unless we can, instead of using the world communicator, can break them off into subsets. And we can do that with communicators. Now we can have the barrier use a communicator that's only for the ocean PEs, and the land PEs, when they're doing their broadcast, can use a barrier that's only for the land PEs. And now, even though it's a collective operation, the collective that's required to be involved is a subset. So we'll see how that works. So they're very important for doing all kinds of algorithms where things go off on different branches, and you want them to be able to do collective operations, but you don't want everybody, by definition, the whole world, to participate. We'll find out that they also give us this nifty capability to start to capture the topology of our data, which is a way of saying the relationships between PEs, who our nearest neighbors are, is the most common one, because as you're already getting a clue with the Laplace code, and some of the examples I've already pointed out, knowing who your nearest neighbors are is very useful in MPI, because that's often who you want to exchange data with. And we can capture that information. I'll step you through some examples. And so anyway, let's get to the example so I can show you how the communicators work. But first, how do we define a communicator? How do we make these subgroups? And there's two basic ways in MPI to come up with subgroups. The first one is to use some of the group routines that MPI has to create a group to tell all the PEs to participate in it. And so here is an example of a simple code where we want to have all the PEs except PE0 participate in a reduce operation. So we want to have a reduce, but PE0's got other things to do at that point in time, theoretically. So we want all of the worker PEs to do this reduce thing here. So we need to have a communicator that's not MPI COM world. Here's a reduce that all the PEs participate in. So it has MPI COM world. All the PEs, including PE0, call this reduce. But here's a reduce that only PE0 participates, or everybody but PE0 participates in, right? If PE0 skips this reduce, which means if we had MPI COM world here, this line would hang. But all the PEs would come in here and try to do the reduce, and they'd be waiting for PE0 to participate, and it wouldn't, so this code would hang. But we're going to define our own worker communicator here. And this worker communicator here is going to not include PE0, and so this will work just fine. So how do we do that? Well, we have a bunch of commands. I'll go through a brief list of them on the next slide that allow us to manipulate groups. So the first thing you do is you create a group from some existing communicator. So we only have one communicator at the beginning of this code, the world communicator. So we'll grab the world communicator into a group. Now we can manipulate this group, and we have lots of different commands to manipulate the group. I'll go over, like I said, the next slide, some of them, but we're going to use the exclude command here to exclude one of the PEs from the group. So we're going to exclude these ranks from the group here. So if we go up here and look at what ranks we're excluding here, this list is a short one, it's just PE0. So we're going to exclude PE0 from the group. So that's what this group exclude is going to do here. At this point, we've got a group we're happy with. We can manipulate the group as much as we want, but we're happy with it at this point. So we're going to create now from this group a new communicator. So we can create a new communicator from this group, and we're going to call it the workers communicator. So now that we have this workers communicator, when we're down here in our situation where we want all this collective to only apply to the workers, we're good to go. We've now got a workers communicator. And here, where we want to use all the PEs, we're also good to go. PE0 can participate here. And once again, with these kind of things, especially if you're going to do it dynamically, create groups and whatnot, you theoretically should free them when you're done. It's not so important if you create them once in the whole code. If you had an oversight here, nobody would notice. But there are situations where you want to dynamically create and eliminate groups. And MPI is very efficient, and it's happy to do that. In which case, you want to make sure you free the groups when you're done with them. So here's the ability for us now to take and have collective operations only apply to a subset of PEs by manipulating groups. And then the group manipulation commands are, I think, pretty intuitive, and they're very flexible. I don't think you have a problem creating any group that you want to. You can just include and exclude PEs and do different things. So it's very easy to make the right group. The other way to create groups that's very common is to work directly with the communicator, to not use the groups really at all. To just take a communicator and split it into subcommunicators, into subgroups, but directly into subcommunicators. And the ability to set things up so the split command does exactly what you want is quite powerful in MPI, because it's based upon something that's usually referred to in documentation as a color and a key, but that's just basically a way of saying, before we do the split, we can assign every PE to its own subgroup so that they all call the split, and when they walk away from the split command, they all find themselves in different groups. So to reproduce the functionality of the previous group-based communicators, we could do something like this here. we could say if I'm PE 0, then my color equals 0. Everybody else is going to have a color of 1. So they're all walking into the MPI comp split with a different color. Well, they're two different groups, really. I mean, they're all walking in with either 0 if they're PE 0, or all the other PEs have a color of 1. So after they call this comp split, they're all going to end up with a different PE, or excuse me, a different communicator here. It's going to have the same name. It's all called comm workers, but the workers version of this that's assigned to them will actually be a different one than PE 0. And so basically we're doing the same thing as we did in the previous code. We now have a communicator that the workers can use that won't include PE 0. The key argument here allows us to actually control the order within that group. You might ask yourself, after you come up with a new communicator, whenever you use a communicator, it has its own numbering scheme, its own ranking scheme within that communicator that goes from 0 to however many in that communicator. For example, we know that the comm world communicator, the PEs are ranked from 0 to however many PEs there are. So if we have 8 PEs, they're going to be ranked from 0 to 7, right? That's the way that the world communicator and the addressing scheme works. What if we split those 8 PEs up into odd and even PEs? So we come up with 2 new communicators, one called odd and one called even. What will happen is that in those new 2 communicators, there's a new addressing scheme that goes from 0 to 3 in each one of those communicators. So the odd communicator, it has addresses when you're using that communicator from 0 to 3, and the even communicator has addresses from 0 to 3. So whenever you have a communicator, it's always got its own separate addressing scheme within that communicator that goes from 0 to whatever. Well, you might be happy with whatever randomly gets assigned to that group, and that's quite often the case, but you can also control it with key. So you can use the key to say, when you split this thing up and you come up with new communicators, I want PE 0 to have the new rank of 0, and I want PE 1 to have the new rank of 0, and I want PE 2 to have the new rank of 3, and I want, so you can control within the new ranking scheme the addressing, the address numbers, basically. I hope that makes sense to everybody. Let's see, no comments. Okay, another thing I said communicators can do that's very, very useful is to keep track of who your neighbors are. Is basically the most important one. To keep track of the topology, the relationship between you and your nearest neighbors. Because you know, doing a data decomposition is the most important and the most thoughtful step, typically, in creating an MPI code. You're, I won't say struggling, but you're dealing with that right now with the Laplace code, right? You got to keep track of who your neighbors are and all those indices and whatnot. And it can be very nice to offload that bookkeeping to MPI, especially as your codes get to be realistic and large, because the Laplace plate is very simple. The 3D Laplace code gets to be a little more complicated. In the real world, for, I'll say, thermodynamic modeling, like we're doing, nobody cares about a square metal plate. They care about a turbine blade with its twisted shape. You know, you care about the cooling fins on the heat exchanger on your CPU cooler. You care about weird shapes. Those weird shapes, when they turn into finite element meshes and things like that are very irregular, your domain decompositions become odd and weird shapes. We'll look at a few examples of this a bit later. But in the real world, things are not only 3D, but there are weird shapes, and the boundaries between things, your neighbors and their halo zones, are weird shapes. And doing all the bookkeeping for that can oftentimes be the biggest part of doing your MPI port. And so in the olden days, people very usually often did all of that bookkeeping themselves. And it's in some sense straightforward, but it's still a lot of coding to do. You know, when you got to find an element mesh, and, you know, your neighbors are kind of weird steps like this. You know, keeping track of who's neighbors with who is a lot of code. MPI can help a lot with that. And I'll show you how the communicators do that. So let's take a look. There's 2 classes of them. One for when you're dealing with Cartesian or nice rectilinear coordinates, and a more general one for when you're dealing with any odd shapes. We'll step through them both here. So let's say you're dealing with Cartesian coordinates, much like our Laplace code, for example, where you've got, in this case, we've got a square metal plate, and we've broken this one up into a 4x5 pieces. So this could be our Laplace problem, except we're running it as 4x5 pieces instead of a bunch of strips. So we've broken into these 4x5 pieces. We can create a communicator that actually knows how this stuff fits together. And the Cartesian create is the right one to use whenever you've got Cartesian or rectilinear type coordinates. And all we do is tell it the details about this, this grid. We tell it how many dimensions there are, and for each dimension, what the extents are. So we've got 5x4 grid here. We tell if it's periodic. MPI is nice. A lot of times you want periodic boundary conditions so that the neighbor for this border might be over here. MPI can keep track of that. In this case, we're saying it's not periodic. And then we can create this new communicator. And so this communicator now knows, it's aware of this stuff. And when you do the create, it can do a lot of smart stuff for you. It can make sure that the PEs are the best neighbors based on the underlying network that's involved here. It can deal with the fact that if you've got odd numbers of PEs involved here that don't fit the grid, it can leave some of them kind of out of the thing. It can deal with the fact that if you don't have periodic boundary conditions, when you go to send a message in this direction, it shouldn't send any message at all, or it could send it to MPI null. So it'll take care of all those details for you. It saves you an awful lot of logical coding, you know, if on the edge, do this. So and here's how it basically keeps track of that stuff for you. In this case, we defined our grid in the previous communicator, and now we want to know who our neighbors to send to the left are. So we want to know, what do we do when we're sending to the left and when we're receiving from the left? So that's a Cartesian shift, a shift in the left direction. So we call Cartesian shift with our new communicator, and we say which direction we're going in. And the directions work here in 2 dimensions, but they'll work in 3 dimensions or even higher dimensions just fine. So we tell it what direction we're going in and how far we're going, maybe displacement of 1 here, -1. So this tells us so the direction is actually the axis that we're working in, and the displacement is how far we're going in that direction. So we tell it we want to go this direction, left on this 2D grid. It will come back and tell us who our new source and who our new destination is. It will let us know who we should be receiving messages from and who we should be sending messages to. So we don't have to do any of the math of, 20 mod 4, 20 mod 5 to get the X and Y coordinates, and maybe this is running on 26 PEs and we want to ignore 2 of them. It'll do all of that math for us, and it's just as simple as this. We set up the communicator, and now we say who are our neighbors to send and receive from in the X direction, and it does this for us. And if this is on the edge, it'll automatically say your destination. It'll fill it in with MPI proc null. So you can see how convenient this is for dealing with that bookkeeping. And there are other associated routines too, in the event that you want to do more detailed things, which is not uncommon, like find out a plane, for example. You might want to communicate with a slice or a plane in a certain dimension, and you can do that. So these routines give you the ability to not have to do all that bookkeeping code. Now, as I said, life is not always Cartesian, and in the real world, it's very often irregular. And this is where the graph topologies communicators become useful. And whenever I say graph, by the way, people think of something that's completely arbitrary like this, but the real world can have graphs that are pretty regular looking, but still are graphs like this. Maybe we've got a Laplace code where we care about the values of the diagonal elements as well. And so we might care about things that are harder to find Cartesian coordinates. And so graphs allow us to do any kind of arbitrary geometry we might want to. So this is a graph, so is this. And to capture those in MPI is very easy. There is a very old and deprecated way of doing it, which you probably will never care. You'll never care about, and you probably won't even come across. It's very old. But there's 2 generally useful and common ways of doing this. One is if you want to set things up, and every PE knows who its neighbors in the graph are. But sometimes setting up graphs and complicated data structures, if you've got a big, large, complicated finite element mesh that's very irregular, finding out and dividing it up, doing the domain decomposition, and knowing who all of your neighbors are might be the hardest part of your code. It might be a lot of code devoted to doing a nice, even distribution, because you want things to be balanced. You want to have roughly the same number of elements in each one of the PEs. And so that can be a big part of the code and a lot of the logic, in which case, one of the PEs might be doing all that math and all that logic, and it knows what all the arrangements should be. And so it's going to be responsible for setting up the entire thing, in which case you use the general graph interface. I'll show you an example of how these 2 work. So here's the adjacent graph interface. This is where each one of our PEs knows who its neighbors are. So for example, PE0 here knows that it's got 1 incoming neighbor that happens to be PE4, and it's got 1 outgoing neighbor that's PE3. So all the PEs have these arrays knowing who their neighbors are and who they're sending and receiving from. And then they all call this graph create. And then they all walk away with a communicator that has all this knowledge now embedded in it. And we'll see how that makes life very easy for communications in a few slides. But the communicator now knows all of these relationships. So this is how the adjacent graph interface works. It's as simple as this. Every PE says, I know who my neighbors are that I'm sending and receiving from. The general graph interface is where, as I said, only a subset of the PEs know the general arrangement. In this case here, for example, only PEs 0 and 4 have that knowledge, and they can still set everything up for everybody. So PEs 1, 2, and 3 don't know, they haven't calculated who their neighbors are, and that's fine. They've left that up to PE 0 and 4. PE 0s and 4 know who all the neighbors are and who their inputs and outputs are. And so they've defined the same grid as the previous slide, only now it's only a couple of PEs that are doing all the work. And that might be a useful way for you to actually do your domain composition. Very often in this situation, it'll actually be really one PE does all the calculation and sets up the whole grid, and that's fine too. So once the communicators have all this information, they can do a number of really clever things to keep you from having to worry about the bookkeeping from there on out. They can tell you at any point in time who your neighbors are, which can be a useful thing. And by the way, these neighbors can also have weights associated with them. You can even have strengths of these connections in the network. So a network not only has a connection, it might even have a weight associated with it, and which is not as common, but a capability that's there. So you can find out all that information for who your neighbors are at any point in time. But most important, and this is where it gets really amazing in terms of cleaning up your code and making life easy on you, you can now take all of that complicated communication that, if you think about being a PE in the middle of this crazy graph that's trying to capture a finite element mesh, your logic would have to be to say, exchange data with your neighbors. You'd have to step through all the graph and look at who your neighbors are and send data to each one of those neighbors. And those neighbors do the same thing with you. They'd have to step through the whole list of who the neighbors are. You can instead reduce all of that to one single call, an all gather, which basically, if you step through and read very carefully how it's defined, at the end of the day, acts like, hey, I'm going to broadcast to all my neighbors and they're going to broadcast to me, because it already knows that Communicator, it knows who all your neighbors are. And so it knows to send the data to all of your neighbors, and it can collect the data from all of your neighbors. So this is the real huge win of going through the graph topology and setting it up, is once you've done that, most of your communications with your nearest neighbors turns into a single call. So here's one that's even more flexible. Again, if you read through the description, you have to read it a few times to kind of make sense of it. But what it amounts to is this will allow you to also communicate with all your neighbors, but even send different types of messages to each one of your neighbors, or different amounts of messages. So the bottom line being that after you set all of this stuff up, your communication and your code actually turns into one nice, simple MPI call. And so think of how much nicer that is than all the bookkeeping you would otherwise have to keep track of with an irregularly structured finite element mesh. And it'll deal with all the things like where there are proc nulls for PEs that don't exist on boundaries and whatnot. So this is a very, very nice way to clean up your code and take care of the bookkeeping. And there are more complex versions of these. You might want to send varying counts to your neighbors. You might want to send different types to your neighbors. So you can even have, you might want to send, for whatever reason in an algorithm, to one neighbor might receive a float and a character string, and another neighbor might receive a string of integers. You got a lot of flexibility to do that. So you have the ability to, again, include extremely complex messaging patterns into a single call, then, because you're going to do it over and over in your code, makes your code a lot cleaner and keeps track of all that bookkeeping. So, because again, in the real world, these are the kind of things you want to picture. I'll come back to this example later on, but basically, here's a very small condensed version of a seismic modeling code. So we did the seismic modeling code. We're trying to model earthquake propagation across the surface of the Earth. It's a very, very important application with a lot of real world implications. And so we're trying to model the earthquake propagation here. The Earth is made up of a very irregular geology. And it's important that you have a grid that captures dense rock and loose soil and things that are in between. And so when you end up with sticking into it, the physical problem, it turns into a very complicated mesh, which is what this red thing is from the edge. It's a very complicated mesh. Now you want to break this mesh up across all the PEs. You'd like each PE to have roughly the same number of elements, so they have the same amount of work to do. If you don't, if you were to break the mesh up, say, just into a bunch of cubes, then some of the PEs might have way more elements in them where it's dense, and they've got a lot more work to do. And so it's very inefficient. Every time step, then one of the PEs might take a lot longer than the other PEs. So you'd like all the PEs to have roughly the same amount of work. So every time step, they get finished at roughly the same time and can move on to the next time step. And so when you do that and you balance it all out, you end up with something that looks like on the bottom down here, each one of these colors here represents a different PE, a different PE's piece of this mesh. And you can see these some pretty irregular lumps here that represent what the PEs are. And that means they're neighbors. And this type of technique also uses the same halo scheme, the same ghost zones on the edges to communicate with their neighbors as the waves propagate. But you can see here the edges that they're communicating with their neighbors are very irregular shapes. And so when we did this code, this is a somewhat older code, we actually did all the bookkeeping ourselves. So this particular code does all the bookkeeping. It didn't use these collective routines. And a huge part of the code was keeping track of all this kind of, you know, who each one of the neighboring cells is in each one of the neighboring PEs and who you communicate with. But with these collective operations, that would have cleaned up and simplified our code an awful lot. And these operations have been around a while now. This code is good at this point in time. Wow, it's coming up on not quite 20 years old. So this is it's grown since then and adapted. It's a much more modernized code now, but we used to do all the bookkeeping. Now the obvious way to do this would be to do it with collectives. Makes life much simpler. Okay. There are a lot of little features in communicators. You can even create, you can add in new PEs to the groups and redefine things as we go. I won't dwell on this because it's not that important. But the summary for the communicators is here. I hope you can see that they allow us to not only do collective operations, the many collective operations you have in MPI, on subsets of PEs, which is really important. Like I said, you can't have some of the PEs go off and do a barrier operation on their own unless you define, you know, new communicators for those collective operations. And I hope you see they can also be great ways to help organize your code and deal with the topology. So they're very, very useful things, and you're going to find yourself using it. Okay, on to the next important topic in more advanced MPI, and that is the fact that we have things to do besides the blocking sends and receives that we've been utilizing thus far. Now, the blocking sends and receives, there's a reason they're the kind of default starting point in MPI, and that is because they do a lot of nice things behind the scenes for us. In particular, they worry about the fact that if we send an array off, that we can immediately thereafter in our code go ahead and use the array A and manipulate it, safe in the knowledge that a copy is being sent on its way. And that's a wonderful thing. But we saw that that comes with a little bit of a price, or we've started to see it comes with a little bit of a price. It has to make this extra copy of the array. That takes some time. If the array is really huge, it could back up and block. So there are other MPI routines that are a little more efficient and don't run into those problems. They come with the price of a little bit more, tracking on our part, a little more responsibility that we have to take. So here's what non-blocking message passing can do for us. We know yesterday I mentioned briefly when we talked about this mechanism that we could potentially run into a problem like this where the messages block, where if we have very large messages and we're sending a message between P's 1 and 0, they're exchanging messages. They could, if the messages get large, this send tries to send a message to PE1, but it's huge, so it's going to back up until PE1 can actually receive the whole message. Meanwhile, PE1 is doing the same thing to PE0, and so they're going to deadlock. That's the term that's used in this kind of circumstance. They're going to block, and the code's going to hang. And we can even see this with the Laplace code. This isn't strictly theoretical. Laplace code, for example, we're doing this kind of exchanges right here between ghost zones. And so with the Laplace code, they are all trying to exchange with their neighbors at once. What if the code, the buffers are large enough that they trigger this problem? And by the way, this is something that actually happens on real machines. On Blue Waters, which was a machine until recently at one of the supercomputing centers, whenever we went up to a 10,000 by 10,000 array, which is something we do in some of our classes here, we make the array bigger to make it a more challenging problem, we'd run into this problem. That if we just did this kind of coding here, we just tried to send everything at once, it would block and would back up and it would hang. So you can run into this even on huge machines at relatively modest message sizes. So the answer is, there are a couple different things you can do. One answer is you can start to think about the problem. You can say, instead of trying to receive at once, I can do a send to the left and then receive from the right, and I can unblock things like this. So if we rearrange the lines like this, then everybody sends to the left, except PE0 doesn't have anybody to the left. So PE0 is still free, it isn't hung. And so PE0 now can actually receive the message. So it can receive the message and send to the right, and that unblocks everything. And then this chain will unblock and it will actually work. So you can think about the problem. Now, this isn't real efficient. Everybody still had to wait for things to unblock instead of simultaneously exchanging. and it's still error prone. So you can try to think your way out of the problem, or you can do the smart thing, which is just go to non-blocking message passing. By the way, along the way, you might notice that there's also amongst the MPI routines, there's a send receive routine that does this in one fell swoop, because this case is so common of trying to exchange with your neighbors. This will actually not block also. This will solve our problem as well. So we could do a send receive. But in general, the way to not worry about these problems is to use non-blocking routines. So this is very, very common in MPI. And as you gain more experience, you might just start writing your codes with non-blocking routines from the get-go. That's what I typically do these days, is I just write the codes as non-blocking MPI. Although converting from blocking to non-blocking is very easy, as you'll see as well. So while you're still kind of gaining some experience in MPI, it's a reasonable thing. Write all your code with blocking sends and receives. And then as you start to concern yourself with bigger messages or places where there could be deadlocks, or you don't even want to think about it, you can convert them to blocking or non-blocking sends and receives. And here's how easy it is to convert to those, and here's how easy it is to use them. The non-blocking versions have this I in front of them. So we have MPI I send and I receive. And the only difference is they have the same parameters if we step through here, except the last parameter, we have a new parameter here. The last parameter is a request parameter. And it tells us when the command is actually executed, because both of these commands are guaranteed to always return instantly. So the I send will always come back, even if the message is huge and hasn't been sent yet, it won't hang, it will come back. And we have to, it's our responsibility to check this request flag later on and make sure that it has been sent before we go and mess with this data. Just like the receive will never block. Even if there's no message that matches, it won't wait for it, it'll come back every time. And it's up to us to go back and look and see, hey, did this message ever actually arrive? And is it sitting in memory, and we can now use that data. So these request flags are a little extra responsibility that come with these non-blocking routines. But we can easily check and see when finally the commands have been executed. And we can do that with these test and wait commands. We can test to see if the flags have come back. We can test a particular flag. We can test all the flags, because very often you'll do this with a bunch of messages. In our Laplace code, even right now, for example, we're receiving messages from above and below. So when we do a receive, we could say, hey, receive from above and below, and we could look for all the, we get an array here. These requests become a little array, and we can check and see, did all of our messages come in yet? So you can look for one message or all of them, or even some subset of them with test sum. And you can just, instead of testing, you can actually just say, hey, just sit here and wait, because I need the data before I move on past this point. So I'm just going to sit here and wait for the messages to come in. And you can wait for all the messages or some of them to come in. So these are very useful and easy to use commands. So here's our shifter exercise that we did yesterday. We just sent a message to our neighbor, except here we're doing it with non-blocking routines. So the MPI code is the same otherwise, only now I'm going to go and convert my sends and receives to I sends and I receives. So when I send to my neighbors, I'm doing the same thing as before, only now I want to capture these request flags on the end. And again, typically you do this, you capture these in arrays here because you have multiple messages coming and going. So I'm going to check and see if my request is executed, or my receive request is executed. I'm going to check and see if my send request is executed before I finally go and print things out. So what I'll do is I'll send and receive these. Now, theoretically, if I had other things to do, and very often in codes, you have lots of computation going on, I could go ahead and do stuff while I'm waiting for these messages to execute, because these are never going to block. So I send and receive, and I wait for them to finish, and I could do other things here. And then when it's finally time to print stuff, I do want to make sure that stuff comes in. So I'm going to sit here and wait before I print things out on these two requests to complete. And when they finally complete, when the message is finally, what I really care about is the receive. When the receive is really complete, now I can print out the value here. So you can see how easy it is to use these things. Here's a Laplace code that was used in our summer boot camp. We have a hybrid challenge where we have competitors that use the bigger problem size, a 10,000 by 10,000 Laplace problem size. So you can write the fastest version of it. And here's a very clean and elegant way that they did overlap some computation and communication. They recognized that after they did the computation of the new Laplace values, that would be a good time to send and receive the messages. And it's the kind of thing you're probably discovering right now as you're implementing your own communication phase. You're probably sticking in a lot of sends and receives here. But they also realized that while those sends and receives are going on, they could go ahead and do the next step here, which is copy temperature to temperature last. So they're overlapping the computation and communication while the message passing is going on in the background. And then here at the end, before we move on to the next time step, we best make sure we actually receive those messages. And so here's a nice way to overlap some computation and communication. And so this is a very desirable thing to do in almost any MPI code and almost any parallel code. You've got communication and it takes time. Very often it takes a substantial amount of time. Not unusual for it to take most of the time. Might be communication in your code, depending on how fast your network is. And so if you can hide some of that communication by doing something useful while it's going on, that's wonderful. And these non-blocking sends and receives make it easy enough. The opportunities there, they make it easy to implement at least. And so that was used here by somebody knowing the Laplace hybrid challenge code. Okay, and you can mix and match non-blocking.
John, I lost you for about 5 seconds.
Whoops, I heard a little audio there.
Yeah, you're back.
Back? Oh, it's breaking up. Sorry. Okay. So you can mix and match, and that's useful because, oops, now I see that message. My connection's unstable. So
You're still good.
Okay. Okay. The message always seems to come just too late to be useful. Okay. So you can mix and match the sends and receives, and that's nice because it allows you to easily evolve your code. You can write the whole code using blocking sends and receives, because that might be the easiest way to get it off the ground and debug it and make sure your messages are going where they're supposed to. And then if you want to make it more efficient and you want to avoid any potential deadlock concerns in the future, you can slowly turn your code into non-blocking sends and receives. It's very easy. There's even a non-blocking barrier. People sometimes get confused as to what sense that even makes, but it can be useful at times, because sometimes in your code, you'd like to have a way to make sure that all the PEs have gotten past some point, but you don't want them to waste their time sitting at that point. So you can throw in a non-blocking barrier, and then you can see that all of your colleagues, your fellow PEs, have actually gotten past this point in the code. So you might be able to do something you couldn't otherwise do, but without everybody having to waste time actually sitting at the barrier. So they get to move on, but you can know when they're past that point. So non-blocking stuff is great. Now, the non-blocking stuff starts to save us these buffer copies, because we don't have to do the copy into the send buffer if you're using a non-blocking send, because it's saying we're responsible for not messing with the array A before it's sent. And so it doesn't have to copy the array A. And this copying of stuff, huge data structures around, can be very expensive. So using the non-blocking sends means MPI doesn't have to do any of this copying. It can just try to send it directly from memory here to the receive buffer and skip this copy. And it's up to you to not touch this memory, mess with array A until you check, you test and make sure that it's been sent. So that's a benefit of using the non-blocking stuff. But we can even take this a step further. We can now go from the non-blocking stuff into what's called single-sided message passing in MPI, which is where we don't really want any sending and receiving buffering to go on. We'd like to just go and stuff something into this array here in memory on the other side without anybody having to worry about receiving it on this side. Or likewise, we might want to go and get this array A from this memory right here and just pull it into our memory here without this PE having to participate at all. And a lot of times, really, at the end of the day, that's all you want to do with your parallel code, right? You just want to get this array here to here. And you don't want any more rigmarole than necessary and any more copying than necessary. You just want to get from here to here. And the single-sided communications allow us to start to do this in the most direct way possible. Again, with a little more responsibility that things have actually happened, and because when things happen magically, somebody's stuffing things into your memory, you need to be paying more attention before you go ahead and use variables. You can make sure that things are at the state you think they are. But otherwise, performance-wise, it can be great. And it can sometimes simplify your algorithms a whole lot. For example, let's say here we have a global counter somewhere that keeps track of, let's say as we're reading in data on our PEs, some of the data is bad. So we want to have a counter somewhere to keep track of bad data points. And we'd like it to be a global counter. So somewhere we'd like PE0, for example, to know how many bad data points all the other PEs have encountered as they read stuff from disk. So PE0 is going to keep this counter. Well, with the basic MPI blocking sends and receives we'd have to have like PE0 sitting there all the time waiting to receive an update message from the other PEs. It says, I received a bad data point. Here, update your counter by 1. And so PE0 would have to sit there polling all the time. It would kind of, be dedicated just to that. It would be nicer if the other PEs could just go and update that variable in PE0's memory and just treat that as the global counter. Well, that's where the single-sided communications come in. It allows us to start to do things that we couldn't do otherwise. So it helps. Most people, I think, usually it just helps in straight up performance because it avoids some of this unnecessary buffering and copying, but it can also help algorithmically. So let's see how it actually works. The MPI put and get commands are the ones that allow us to do this direct stuff, and we can skip for all this extra buffering and whatnot. So here's how they work. Is basically, to use the most basic versions of put and get, we have to define the windows in our local PEs that are allowed to be used. We can't just go and stick things willy-nilly into some remote PE's memory. It needs to tell us where we're allowed to modify data. We call them windows, and that's a fancy way of actually saying variables. So we're going to name some variables in our memory that other PEs are allowed to access, and we're going to let other PEs know about those variables. Then, with those variables are allowed to access, we can move the data using puts and gets. And after we do that, because it's all happening behind the scenes, our code might not even be aware. So we've allowed some window on an array to be updated. Well, how do we know when the data is done moving and we can use it? Well, we need some way to do that. So let's see how that happens with our Pi code. So here's our Pi code that we were doing yesterday, except now we're going to do it with the single-sided communication stuff. So I'll step through this line by line, but to give you the quick picture of it here is we're going to define our windows here where we can read and write memory. And in this case here, all the windows are going to be on PE0 because PE0 has got the, for finding our Pi code, you remember there's only a couple of variables involved, one of which was how many iterations the user wants to use, how finally they want to divide up our integration. So they might want to have 1 million slices for our Pi integration. And the other one is our actual answer. When each one of the subtotals for the PEs that find their own my Pi, their own subtotal Pi, they all want to get that back to P0 to be summed together. So we define some windows, and again, we'll step through this in more line by line. Then we do our communications. So we want to get from PE0 the value that the user inputs for n, how many slices. We want to make sure all the other P's can get that value. And then they do the number crunching. And then when we're done, we want to take and accumulate all those values. We want to sum them all back up on PE0. So that's what's going on here. So let me step through this line by line. So the first thing is creating windows. Again, you can't just go and grab any variable on any PE and stick things into it or grab its memory. Instead, you have to upfront create the windows that you're allowed to access, and that's by pointing it at variables. And once again, I'll mention that in real code, you're very often using dynamic memory, things that are created and allocated on the fly. And this is in Fortran and C, the Fortran allocatables and C, mallocs and similar calls. So we want to create things in memory dynamically. Well, MPI is perfectly happy working with dynamic memory. MPI is a very serious library, so it deals with real world cases like that very easily. So if your windows are dynamically allocated, you want to step through it like this. So I won't go into the details, but very straightforward. Once you've got your windows allocated, now you can actually do the message passing. You can put data into a remote PE's memory, and these look kind of like I hope these arguments now make sense to you. It's the value we want to put. It's the count of them and the data type. It's the target we want to put it into, and it's where we want to put it in that target and data type there. So it looks like a send receive kind of combination right here. Get's the same thing. We want to get something from the target and pull it back into our memory. There's one more here, which is called accumulate, and accumulate captures mostly the reduce type operations. And so with reduce operations like sum or min or maximum, we want to pull those back and accumulate them in one spot. So think of accumulate as a different terminology for reduce. You won't be far off. These are the different types of reduce. The MPI operations we use for reduce are the ones we could use here. In our Pi code, for example, we want to add together. We want to do an MPI sum on all the data that we're getting. And there are also non-blocking versions of these that return flags as well. Well, actually, they're all non-blocking, but these are ones that return request flags as well, just like the non-blocking MPI routines that we just looked at. So that's how we get the data. But when we do these operations, we need some way of knowing that they actually occurred. And so fences are ways that we separate our communication, our computation, so we can see when our computation phase is done. So in general, there's some fine details to this if you want to get into it, but in general, you're going to be safe if you just fence off your communication and your computation phases. We'll see what that means in our Pi code. In our Laplace code, for example, right now you're implementing a communication phase, and it's going to happen after you do some of the Laplace Jacobi iteration computation. You're going to do some computation, and then you're going to do some more. You're going to do some communication. And then you're going to do some more computation. So computation and communication phases are very natural things to have in your MPI code. And these fence commands separate them and give you a way of making sure that all of your communications have concluded, because they're all happening behind your back with these puts and gets. And so that's what the fence commands do. And you can even give some hints to the fence commands as to, when things are being, kind of the patterns that are being updated. I won't go into this right here. They're kind of self-explanatory. These hints can help optimize things. I find in the actual implementations, they don't do much at all. So the fence commands, again, if you just stick fence to separate your computation and communication, everything will work fine. It's a little stricter than necessary. If you get more advanced in MPI and experience, you can break the rule a little bit. But in general, we're just going to separate our computation and communication. So here's our Pi code again. Let's step through it here and see exactly how we're using all these commands. So if we're PE0, we need to set up a window so the other PEs can get to our variable for n, which is how many the user inputs, how many steps they're allowing. And they need to all be able to get that. In the past, we did that with a broadcast command, but here all the other PEs are going to come in and get that. We also need to set up a window on the variable that's going to receive the total for pi. In the past, we did that with a reduce operation, but now we're going to have them all accumulate their variables into pi here on PE0. Now, the other PEs don't have any windows at all open. They're going to be just grabbing stuff and putting stuff into PE0's memory, but you'll notice that the window create commands are collectives. And because they're collectives, that means all the PEs need to participate in it. So even though the other PEs don't have any windows they're creating here, they still have to participate in this call. So they're going to call it, and this is where they find out about what's going on PE0. So they all call create, but only PE0 is going to create some windows for real. Okay, so we've got these windows. Now PE0 is going to ask the user how many inputs to have here. And now that PE0 has that information, all the other PEs can find out about it by going and getting it from PE0. So they're going to go into PE0 and get that. But we need to fence that off so they know when they can go there. If we didn't have this fence here, they might go there before PE0 has input the information. They wouldn't know when to wait. And when they're done getting it, we can move on. Otherwise, PE0 might go ahead and mess with this value n here and before it's been captured by all the other PEs. So we fence off the computation from the communication. And now we can go and do some computation here. And now they've all got their partial sums. So we want to fence off this next communication so that they all know now that PE0 is going to be able to accumulate the valid values. So they all go into PE0 and start summing together their partial values of pi. And then when they're done, so PE0 needs to know when you're done sticking your values in my memory, can I go ahead and print this out? Because it doesn't know otherwise, it's just happening behind its back. So the fence lets it know it can move on and it can print out the values. So this is that Pi code, but done with fences and with puts and gets. And so it's more efficient. It's not doing any buffering behind the scenes. Now, in reality, if you run these exercises, this is really no big win because we're not moving a ton of memory and there's not a lot of buffering going on. So this is the kind of code I would never waste my time implementing with single-sided puts and gets. As it was perfectly fine. But that's because we're only moving tiny little variables. In reality, if this were huge integrations and these were arrays and we're accumulating subtotals, and then all of a sudden these puts and gets might be a way to go, but you can see optimizing our code to do it isn't a huge step. It does require a little bit more thinking, but we didn't have to go and rewrite our code from scratch. So you can optimize without tremendous contortions in your code. Now, you might object if I'm telling you this is single-sided. You might object here and say, if this was really single-sided, I wouldn't need all these fence calls in here to keep everybody, between the commands, keep everybody on the same page. I just want to go stick something in that PE's memory, and I don't want it to know about it at all. I don't want these fences. I just want to be able to passively go and modify memory on the other side, and my algorithm can figure out when the data has arrived or when it hasn't arrived. And so there's yet another version of these puts and gets that we can use that are even less linked, I should say, between the PEs, and that's the passive ones. And in the passive ones, what we do is we can go on the targeted PE and lock that window in memory and unlock it when we're done using it. And that PE doesn't participate at all. It doesn't know that we're even doing this. So we take a target PE, PE0, for example, where we're trying to accumulate some values here, or we're trying to grab its value of n from memory. We can go and lock that value on that remote PE and grab its memory from it and then unlock it. And it doesn't even know that this is going on. And so this kind of passive stuff is truly remote. And by the way, that PE needs to lock its own window, even when it's accessing its own n, so that if other PEs are behind its back grabbing things from there, they don't interfere with each other. So we can define these windows now, but we lock and unlock them remotely. The participating PE that has no knowledge that things are going on, it doesn't even have to do fences. And so, and we can once again do this with allocated memory as well. So now we really have a truly passive way of doing, like the counter I talked about earlier, where I said we want to have a counter in memory for bad data, and all the PEs can go and add to it in memory. We now have a way of doing exactly that. It's totally passive. PE0 doesn't have to waste its time polling. So PE0 can be going off and doing totally different things. And meanwhile, it's variable in memory. Its bad value variable in memory keeps getting updated by these other PEs. But this brings us now to some of the more subtle things. When you start to get sophisticated and fancy in parallel programming, you open the door to race conditions and subtle errors that can happen. You're not like, I don't want to make you paranoid, because these are not the kind of things you run into all the time in MPI. But if you start to do fancy stuff like this with remote access, you need to be aware of it. For example, if we do have this remote thing in memory somewhere, we might use it as a flag to lock a file. So we've got this remote counter in memory. We're using it to lock a file. So we've got a file on disk, and we only want one PE at a time accessing that file, because otherwise things can be corrupted. That's a common enough thing to have. So we might say PE0 has the flag for that file. So what I do when I want to access that file is I go and check and see if the file is unlocked. And if it's unlocked, then it's free. Then I go and lock it, and then I access the file. And then when I'm done, I unlock it. And that sounds good. The only problem is, between me going and looking to see if the file is unlocked and me locking it, some other PE might have the same idea, and it goes and checks and sees if it's unlocked. And we both think it's unlocked. So now we both go back to lock the file, and now we both think we have access to that file. So these kind of things are implemented all the time in your operating system or wherever things are operating in parallel. It's called a mutex. So you've got a mutually exclusive flag in memory where you'd like to use it to lock things out. And with MPI, because it has to go off some distance and access that thing to check it and then lock it, the possibility for multiple simultaneous accesses to collide like this and end up with a bad state is very real. And so MPI, of course, has the ability to deal with that as well. So MPI, if you're doing things like that, remote memory, MPI has a single atomic operation. And atomic is the word that tells you this happens in one step. So here's a single step where you can go and set something in memory if it's not set. And it will go and it won't open the window to that simultaneous conflict to happen. So there are operations to do that stuff as well. And this is on the more high-end end of parallel programming. So as you get more experienced and you try to develop libraries, parallel libraries, and truly concurrent programming, this is where you run into these issues. So I just want to point out MPI has all the tools to deal with that built in, but you're unlikely to run into that as just an application developer working on your own science. And likewise, there are a lot more sophisticated, detailed, low-level things for coordinating these kind of operations and keeping them synchronized. But again, unless you're a compiler writer or doing very sophisticated libraries, yeah, you're unlikely to care about it, but you should be aware it's there. Just like there is the ultimate version, there is yet one more version of single-sided access, remote memory access that can be used. That's typically only used by people writing compilers that are parallel compilers. We'll talk about, by the way, at the end of the day in the outro talk, some parallel compilers people use that are built on MPI, alternatives to using MPI. And the people that are writing those kind of compilers use some of these features, but you are unlikely to care about this. And that is for very large scalability, you have these kind of neighborhood-based communication routines. And so we can have routines that only target our neighbors. In other words, if we have 1 million PEs, because we're in the age now of exascale, right? Very, very large machines. You've got 1 million PEs. And if 1 million PEs want to do these kind of remote accesses with their neighbors and target their neighbors, what you don't want to have is them having to be on the same page as to what windows are open with each other. We don't want to have, if we got 1 million PEs and PE 0 and 1 and 3 want to be doing some local neighborhood remote memory accesses with different windows, what we don't want to have is them care at all about what windows are available on PEs 900,000, 900,001, and 900,002 that are out there communicating in their local neighborhood. We'd like them to be completely independent and decoupled. If they have to keep track of each other and what windows are available on all the PEs, that's not very scalable. And it's not necessary, but it's definitely not scalable. And so we have an even version for very large scalable codes that says, I'm going to have a bunch of windows that are open and closed, but I only care about my local neighborhood. We don't have any kind of global tracking of these windows. And so that's where this scalable synchronization RMA comes in. We can have windows that we can open and close on typically only our neighbors, a small subset of PEs. And this is very scalable. But again, this is kind of the ultimate level for people that are writing compilers. You're unlikely to care about that kind of stuff for your application. So I hope that you're not intimidated by all these options now, because they are, as the name suggests, options. You don't need any of them to make your code work. They're just nice optimizations, or can clean up your code as you get to some particular level or have a particular algorithm with certain structure to it. So what you should do as beginners right now is undoubtedly use blocking message passing to develop your code and get it off the ground and get things working. Then, as you find that you might want to optimize a few particular routines here and there where some time is being spent. And by the way, how do you know where time is being spent? You could use manual timers, which are never a bad idea. And I'll talk about those in a moment, but there are also profiling tools. And the tools talk at the end of the day, I'll show you how easy it is to figure out where your code is spending its time. So you might profile your code and find out where it's spending time and decide, hey, these couple communication routines are really, I don't want to do this buffering. They're huge messages and I'm sending a lot of them. So if I can avoid some buffering here, I'll tune these. You can go and just take a couple of your MPI routines and turn them into non-blocking. And that's very easy to do. You don't have to turn them all into non-blocking. You can mix and match and do things where it's important. And you might say, hey, I'm really a more advanced MPI programmer here, and I really want to optimize this even more, or I'm writing this algorithm and I recognize that just from the get-go, I'm just putting data into my neighbor and I don't need to worry about any kind of other coordination. You can go with the single-sided, these remote memory access versions of the routines using the fences very easily, and you can convert to that if you want. And then you can get even fancier and say, hey, I really want to use the passive ones, or I'm super duper fancy and writing ultra scalable code to run on 200,000 PEs and I want to use it. You can evolve your way to this very painlessly. You don't end up regretting that you chose the wrong one and you have to go back and rewrite your algorithms in your code. These are typically nice, smooth evolutions in your code, and you can incrementally go and add this to just a routine here or there. And even when you add them to a particular routine, you're not rewriting the whole algorithm. You're not like, oh, now I've got to rethink the way I'm doing this communication pattern. No, instead you're going and just kind of upgrading a few of the calls here or there. So do not be intimidated by these options. Do not feel obligated to use, scalable synchronization, or you're wasting everybody's time and writing an inefficient code. That's not the case at all. I recommend that you start out with blocking message passing. As you get more experience with MPI, you might start out with non-blocking message passing. As I said, these days, I'll typically just use non-blocking message passing out of the gate because it's easy enough to use. And you might get there very quickly, and you might feel comfortable doing that right now because it's not difficult to use. But don't feel obligated to master all of these or feel you're making bad decisions. It's not the case at all. It's a wonderful thing about MPI, actually, that it has this characteristic. You don't have to make a commitment up front or you'll regret it and spend a lot of time or effort. Okay. Not a lot of questions here, so I'm taking that as a good sign that I'm making sense and not as a sign that the chat channel is dead. Okay. Now we're going to go on to some more diverse topics here. Those are the big things we've covered right here that you're all likely to come across and want to use. But now we'll have got more of a grab bag of things that I want to at least make you aware of. MPI is very, very good at mixing with other programming models where it's useful. Or I should make it more to the point that other programming models, as people develop them, they recognize they better be interoperable with MPI if they want to be taken seriously. So everybody that's trying to do other types of programming models, make sure that they work with MPI, and that indeed is the case for the ones that I think you're likely to come across, like OpenMP and OpenACC. They do work very well with MPI. So here, for example, if you're familiar with it, I'm not going to assume that any of you are familiar with OpenMP or GPU programming, for example. But if some of you are, this shows you how easy it is to mix that in. So for those of you that are familiar with OpenMP, for example, which is used to do multi-core programming, I did talk about this yesterday, right in our intro talk. I said where it fits together. I said OpenMP is when you want to do multi-core programming on a single node, you can use OpenMP. Well, if you're using OpenMP, you can combine it with MPI very easily. And here's an example I did just to make the most complicated version. Here's where every single OpenMP thread is doing its own independent MPI communication. So if you want to have every OpenMP thread send and receive messages, you could do that. And that's exactly what this example does here. I won't dwell on it because I'm assuming for a lot of you, you don't understand OpenMP, and that's perfectly fine. And you may never, with your knowledge of MPI, care that much about OpenMP. You may be able to just use MPI everywhere. Dynamic process management. This is the notion of starting and stopping PEs as the code's running. So far, we've assumed that the number of PEs you get is static because when you type MPI run -N8, that's how many PEs you have to work with for the run. But what if you're on a machine that allows you to grab more PEs as the code's in the middle of running? That might be useful. There are lots of there are algorithms you can think of where the amount of work is increasing as the code runs, and you might want to grab more PEs. Or maybe as the code's running, you've done work and you want to release them back to the pool for the rest of other people to use. And that's dynamic process management. And that would be nice if things work that way. In reality, most systems just can't allow users to, in mid-run, grab PEs. And so in reality, dynamic process management is not very interesting. It's just not permitted on most systems. So who cares? But it is a capability MPI has. MPI does have the capability for you to spawn and add new PEs in mid-run, in which case you get a new communicator back. You get a new communicator that replaces the old world communicator, right? Because you've now got more PEs. So you get this new bigger than the world communicator, basically. So you can theoretically, add and release PEs. In reality, again, that's not really permitted just because it's not a sane thing to do in most operating environments and most multi-user environments. I/O is something that, let's see, I've got a question here popped up. How hard is it to be practiced to change the code from one approach to another? I start with a synchronous message passing, running the scalability problems. How can I practically change the approach now? Okay, well, I don't know when that question came in. If it came in before or after I emphasized, the answer is it's very easy to move between these. And so I guess I did answer that. Okay, so I won't beat that one to death. Okay, I/O is something I mentioned yesterday. It sounds kind of boring. People don't like to talk about it a whole lot until you actually write a successful, fast code, and then all of a sudden it becomes important because you have a hard time feeding, your faster code data fast enough or offloading the data, and all of a sudden your code profiler or your timers tell you you're spending 60% of your time waiting on the disk system, and that's no good. So parallel I/O is something that was rolled into MPI with MPI2 a long time ago. This is maybe the only misstep that MPI has made. As I said, MPI is a fantastic standard, and the committee pays a lot of attention to making sure things work well. But MPI-O was one thing that was a little bit of a step too far, in that it sounds great on paper. So MPI-O are some I/O-based routines that take advantage of the collective operations and the data types that you've got built in. So they allow you to do some really nifty stuff, like say you've got an array that's scattered over a bunch of PEs, like our Laplace code, and you want to output the entire Laplace metal plate, even though it's only a sub. So we want to write out our Laplace metal plate. It's broken up into these 4 strips. And we don't want to write out the ghost zones. Those aren't really valid data, or the boundary conditions maybe. So we only want to write out the sections of the metal plate that are valid. We want to write them out to one nice single disk file so I can go and run off with matplotlib and draw a graph or something. Well, MPI has the capability of doing that in a nice, cool, clear way where we can use the data types that are defined. So we can define a subgrid of the plate so we exclude the ghost zones, and we can do it all at once and keep it synchronized. So it's very nifty and it's kind of nice. Unfortunately, it turns out to usually have performance problems. And here's the reason why. In the real world, this is what a parallel I/O disk system looks like and how it's used. In the real world, you got a bunch of PEs out there with the data. And in real interesting applications, this is not our 4 PEs of our Laplace code. This is 4,000 PEs or maybe 400,000 PEs. And they all want to write to disk. And very often you want to write to a single file, because when I'm done running my code, I want my results for my temperature distribution. It'd be nice if it was a nice single file I could walk away and visualize. I could allow it to write 400,000 separate files and I could paste them together in post-processing, but it's nice if it's one file. So very often, these are all different valid scenarios. You'll come across them all, but very often I have the case where I got 100,000 PEs and I'm writing to one file. And so if I just go and naively do that, I have 100,000 PEs write to one file, I will find out on virtually every disk system that it just comes to a complete halt. It spends all of its time, the I/O system is overwhelmed. It's got too many requests coming in. It's trying to organize them all and lock the file in the right way, because pieces, all simultaneously accessing the file. It'll just come to a halt. So a parallel file system attempts to cope with these things by, in reality, having some intermediate servers that are kind of the conduit, the throughput to everything, and they control the way data actually gets laid out on the disk. They control the metadata that concerns the file layout and how it's striked across all these different disks, because we really have a bunch of different disks that are holding this file. So we've got 400,000 PEs, and we've got it striked across maybe 1,000 different disks here. And these 1,000 disks are maybe coordinated by, well, in this case, we'll say three kind of controllers. In the Lustre file system, which is a very popular file system, it's the one we have on bridges, and a lot of machines have it. In Lustre, these are called OSTs, and it's not really important. That's just a little bit of trivia. These meta file servers kind of control this. Any parallel file system has these kind of these meta controllers in between. It can control the metadata and the layout of the file and the striping and everything else. And so all the PEs actually go through these OSTs, and that becomes a bottleneck. So the OSTs get overwhelmed by all these accesses. And again, your code comes to a halt. Now, there's a very straightforward fix around this bottleneck that MPI is easily able to implement. And that is that since we're using MPI, it is easy for all the PEs to send their data to a smaller subset of PEs. Ideally, maybe one for each OST that you have available to you on your particular file system. And so if I know that my file system only has 3 OSTs, then I can have all the surrounding PEs send their data. They can all send that data to this one PE, and it can write then to the file system. And this will be much, much faster and more efficient. This can often get near the theoretical speed of these file systems, which these days can be, well, we've seen these exaflop systems. If you go back and look at the files, they're a terabyte a second, or hundreds of gigabytes on the big machines per second these days of file bandwidth. But that only works, again, if we kind of corral things down in some sensible way. So the reason that MPI-IO isn't often the answer for using the built-in MPI-IO routines, and the answer is that MPI-IO is not aware of these system-specific things in general, and it doesn't know to do these particular tricks for a particular platform, and it can end up being very slow, and it's a black box, so it's hard to fix that if it is super slow. On the other hand, with MPI, it is very easy to write a piece of code that does exactly this. And I've done this with many a program I've got. And the nice thing about IO, by the way, is that very often in a code, even if it's a large 80,000 line code, the IO routine is separated and it's broken off. And somewhere I go to the IO routine and it's 100 lines of code or maybe less. It does the IO. And then I can stick in with a couple of dozen lines this kind of logic. It's very easy MPI programming. I stick in a couple dozen lines that says, and I even put in a nice parameter typically that says how many OSTs I'm dealing with. And that way, if I go from one platform to the next, I just change this from 3. And if I go on a bigger platform, I can change this to 300 OSTs if I'm on a very large machine. And with one simple parameter now, my IO works very well on that system. So it's a very portable, simple method. It's not a lot of coding, and it works very well. But it's not using MPI-IO. So MPI-IO is there. It's nifty. It's kind of elegant and nice. But I will suggest from experience that doing your own IO routine, just taking your current serial IO routine and tweaking it a little bit, like I just showed, is very effective. Simple to do, doesn't take long, and then buys you really great performance on really great large scalable file systems. So that's kind of the big picture for IO. Okay, enough about that. Let's jump on to another one of these grab bag of topics. Fortran 90 has, as any of you are Fortran programmers, I hope you're using Fortran 90 type notation in your code, because at this point in time, it's now over 30 years old. So it's not exactly bleeding edge. Fortran 90 has wonderful array slicing and shaping commands in it, similar to, so for those of you that are NumPy users in Python, it's the same kind of thing, only it's built into the language. And so it's very clean and elegant. And I hope you use it when you're just writing serial code in Fortran, because why wouldn't you? It annoys me when people don't. It's just a wonderful way to write code. It's also nice in that it buys you some free parallelization and everything else. But at the moment here, what we're concerned about is that if you're using Fortran 90, the obvious way to do things like our Laplace code, where we're sending a strip of the temperature array, might be to stick in one of these nice array slices like this, to say I want to send a slice of the Laplace array. Because why wouldn't you? Fortran 90 makes it so clean and elegant to do that. So if you're writing the Laplace code right now and you're a Fortran user, you might have been tempted to do that, and you might have backed off of that because you said, I don't know, did John tell me I'm allowed to do this or not? Well, the answer is you can absolutely do this. It makes sense, but there's one caution to be aware of here. And that is that if you do something like this, what Fortran does for you as a convenience behind the scenes is it will take and copy the strip of the temperature array out for you into a nice little buffer to give to the iSend routine. And that's nice, good for it. Only problem is iSend, the interrupt driven, the non-blocking send routine, as we've seen, what iSend does is it never blocks, it comes back immediately. Is that breaking up again, Steve? Sort of blip from you.
You lost like 2 seconds.
Okay. What iSend does, as we saw, is it doesn't block, it returns immediately. And one potential problem in Fortran is that when this routine comes back immediately, Fortran, a normal serial compiler, says, oh, you're done with this temporary array that I made a copy of, and I'm going to get rid of it. And the problem, as we see with iSend, is the iSend might not actually have executed yet. The iSend might actually be in the background in progress. It won't be done until it tells us with that flag, and we test for it later on. So if you're using Fortran 90 array slicing, which is great, you should be doing that. Be aware that with non-blocking sends and receives, this potential issue is there. And so MPI gives you a way of testing that. And so you can check with MPI, as of MPI 3 onwards, you can check and you can see if MPI subarrays are supported, in which case the compiler knows not to do extra clever things like this that will mess with MPI. And if you're unsure, then maybe use MPI data types and define the columns and rows like I showed you how to do earlier instead of using these slices. So that's one little issue to be aware of with Fortran 90. But I encourage you to take advantage of Fortran's wonderful mathematical notation. Just be aware of that issue. C++ also has lots of wonderful things about the language that make it desirable. And indeed, the MPI committee made C++ its third officially supported language all the way through MPI 2.2. So the MPI committee is also a huge fan of C++, as am I. Only problem with C++, not the only problem with C++, a major problem with C++ is that optimization and performance depends so much on your knowledge of the details of what you're actually doing, and in particular with the standard containers, with the STL. If you're using the standard template library and all the containers, which people love to use with good reason, you need to be aware of all the things that they're hiding from you, which is kind of the point of these, the containers is to hide details from you. You don't want to know the details of what's going on in there. Only at the end of the day, for performance reasons, not just MPI, you need to know the details. And that is why anybody that cares about performance and is using C++ immediately writes a whole separate rule book about what parts of the language you're allowed to use and not allowed to use. And every company has their rule book. Google has their rule book, which features of C++ you're allowed to use and not allowed to use. All the video game companies have their rule book, features you're allowed to and not allowed to use. Well, the MPI committee didn't want to write a separate rule book of which pieces of C and C++ you're allowed to use, because that just would have been undoable and inappropriate. So instead, they gave up and gave up on C++ as the official third language with MPI. Now, that's not a huge problem because, as any C++ user knows, C++ is effectively a superset of C, not entirely, but mostly, to the point where you can use all the MPI routines we've been talking about just natively. You can just use them all as we've been using them in the class. So that's the typical answer for C++ people. Just use the C interfaces to the MPI routines. However, some of you may be unwilling to give up the niceties of C++ that it brings to MPI potentially. And so there's a boost version of MPI where you can do really nice, clean stuff like this, where you can say, okay, I'm going to send a message using the world communicator to PE1 with a tag of 1, and here's the data. So C++ does indeed allow you to have a really clever, clean interface to MPI that's elegant and nice and awesome. So you can use the boost. If you're a C++ person, you're probably familiar with the boost open source libraries, kind of extensions to the standard C++ libraries, and Boost MPI is a thing. It's been there for a long time. You may want to use that. Boost also has issues. There are reasons people don't like to use Boost. So you may not want to use Boost. You may just want to stick with the C API. It's up to you. It's a decision you can make. It is a shame because it's nifty to get rid of a lot of the boilerplate stuff that MPI requires us to do. I don't care about tags, and anyway. So it's nice and it's elegant, but it's a decision you have to make. These are standard C++ issues, not unique to MPI. Likewise, I said MPI has lots of other language bindings. The only one I guess I'll talk about besides C++ is Python, because this is very popular, and Python. Python, as a matter of fact, Python doesn't have real threading in it, so multiprocessing is really your only option for scalability. That's a whole separate issue, but MPI then gives you a very nice way to do multiprocessing in a way that's clean and well defined. And so MPI for Pi is very, do I have it here? Yes, the MPI for Pi module is a very, very popular library to use with Python. And it makes some very clean and elegant ways of doing things. So here's the standard default way that that the module wraps the MPI libraries, is it will allow you to do things. So here's our Pi code. It will allow you to do things like, here's our reduce operation, is you can just say pi is equal to reduce the communicators, the world communicator. You just reduce, and it's very clean, nice, simple syntax, straightforward to use. However, like all things with Python, if you're really trying to do anything numerical, you want to be using NumPy. You don't ever want to be trying to do any kind of math in straight Python. So you're using NumPy. NumPy has a slightly different interface. It looks more like the things we've been talking about for the past day for MPI, which uses buffers. So it does things in place. So in other words, you'll notice here that our regular regular MPI reduce that operates on the variables that are parameters to it, and our Python version of it returns it as an argument. So pi is returned by the argument. Well, if we use the NumPy versions, it looks more like regular MPI, where everything is an argument in here, because it does things in place on the buffers, and that's required to have any kind of reasonable performance. And so here is, I have a Laplace code. It's entirely done in Python, and I didn't want to cheat and ruin the code for you, so I've only got an excerpt from it here, but this looks kind of like what you're trying to do right now with the Laplace code. And so you'll see here's a send that's done on the temperature array. In this case, it's a NumPy array. So it's an N array here that we're working with. And so here's how to do MPI version of the Laplace code, or at least a fragment of it. Again, I don't want to spoil it for anybody. Performance is much, much better if you use the NumPy, of course, just in general. And if you use the NumPy interface to MPI, you're going to get much better performance. The difference, by the way, is the capital letters. You'll notice this is a capital S for the send, whereas this one, these routines are all lowercase. So this is like broadcast is lowercase b. The NumPy version of it would have an uppercase b. That's the difference between the two. So I think I'm going to the uppercase versions and the lowercase versions. And once again, even with NumPy here, the performance is much, of course, much worse than the C or the Fortran ones, but it's much better than using the native Python libraries, the non-NumPy versions of it. Again, nothing new to you if you're a Python programmer. You know all about those issues. There are many other languages that are supported because MPI is so important. Everybody that has a language out there has decided to roll in MPI libraries, and so they are therefore pretty much anything that's serious has some kind of MPI library available for it. They're not officially, when I say they're not officially supported, the MPI committee makes sure when they roll out versions of either the specification or when people that develop the open source canonical MPI libraries, or we're hardware vendors. MPI is so important that network interface people make sure they implement the MPI stuff well at the driver level. So all of these people, they pay attention to the official C and Fortran interfaces. And then it is up to everybody else to build on top of those and build wrappers, but everybody does. And so anything that's pretty serious these days has some kind of MPI interface to it. These are ones that I'm somewhat familiar with in the sense that I've seen them used and I know that they're at least reliable. But again, these are all kind of independently supported. As for example, MPI for Pi, I know the guy that wrote it. So it's some dude wrote this, you know, and it supports it. And I think these days he recruited a buddy, but it's a couple of guys that support this. It's not like a huge committee or an organization or anything. So you can use them, but just beware that if you got, say, a bug, if you uncover some bug, which isn't that unlikely because you're not part of a huge user base, you know, it's up to you to figure out how you're going to get that supported. You're very unlikely to uncover any bugs in the MPI, the official MPI libraries, because they are so incredibly heavily used by very serious people. So they're pretty robust libraries. Okay. Let's see. Our group ended up programming our own CPM boost. Yes, you are not the only ones. Yes, indeed. A lot of people take advantage of the fact that you can then create your own C++ interface that does the pieces that you care about. So yes. There are a lot of nifty little features I don't want to talk about. I don't have the time to talk about, and I don't want to distract you with and overwhelm you with. So like there are attributes, a little small key store database that's attached to communicators and data types and windows, and you can actually attach any kind of basically a little key store database you could attach to any one of these things if you're writing an algorithm. That's kind of nifty for those of you writing libraries. Here's a thing I do want to emphasize, again, a little piece of trivia, but very useful. There's a fantastic high resolution timer that comes along with MPI. Timers are great things to have in your code. I can't emphasize enough how useful it is to stick timers in different places in your code to monitor how things are going. This is great because if you move your code to a new platform, you can go, okay, my code slowed down by 50%. Why? And if you've got some timers, you can go, oh, the IO system on this machine is terrible. I better talk to the sysadmin and see if I should, I don't know, stripe my IO differently. Or you go, oh, this is terrible CPU performance. I wonder if I should have some different flags on a compiler. So timers scattered throughout your code are cheap and easy to do. Well, I say they're easy, but one of the reasons that they're not easy is that it's sad that there aren't great universal standard timers in codes. There's just so many, everybody's got their own timer and they all have different resolutions, and most of them actually don't even define a resolution. They say it's not guaranteed. You got to check and see how accurate our timers are. And so it's kind of a pain in the butt to stick timers in. Well, once you're writing MPI code, you should know that the MPI-W timer is always at least microsecond or better. It's built in, and so it's very easy to start scattering timers around your code. And it's a simple little timer like this, makes it very easy to time sections of your code. So if I'm writing an MPI code, I always stick some around the communication section of my code, the computation section of my code, and the IO section at the very least. And then, whenever somebody runs the code or moves it or ports it or recompiles it, if something goes wrong, first of all, they know it right away. They go, oh, hey, this thing's taking too long to run. And second of all, they can quickly see at least some ballpark idea of where it is. So stick timers in your code. MPI makes it easy. Okay. I said I don't need to bother you with the history of MPI and how things have evolved and grown, because it doesn't matter to you. It's all one big seamless piece. But I'll give you some very quick rundown of the latest things, although at this point in time, they're not all that new. MPI doesn't change fast these days because it works well, and they don't feel the need to impress people by having fast release cycles that break stuff. Instead, the committee takes its careful time and consideration and only changes things and updates them when they need to be, because when they do update things, they want everybody to implement the full feature set completely. If you release things quickly, nobody can catch up. Like C++ is a good example, right? C++ has all of a sudden decided that it's going from updating once every 15 years to every couple of years, and now it's a big chore to find out what compilers support what latest, greatest features, and the answer is, for some period of time, none of them support all the features. And anyway, MPI has taken a very opposite approach and said, we've got something that works well and it's mature. So by the time we officially release something, it's probably completely implemented already everywhere that counts. And we're not going to release things on a fast cycle. So I don't want to bother you with this stuff because you don't need to know, but I'll give you some idea of some of the things that are out there to at least be aware of. MPI has two kind of families that are out there in terms of the open source community has worked on two very independent bases that everybody builds on top of. So you've got MPitch, and a lot of people build on top of that. So you've got MVA pitch libraries you can grab, or Intel MPI and some other ones. And again, they're all compatible. Every byte of code we've written here today will work between any of these versions just fine. So you don't need to worry about versions. But if you do wonder what people are using to build and on top of, MPitch is used by a number of different groups to build their MPIs. And when they build their MPIs, they sometimes tune them a little bit better to their local hardware, make them work a little more transparently with their compiler. But it's not some compatibility issues you need to worry about. Usually just worry about maybe some minor performance differences. The other family is OpenMPI. And the OpenMPI family is used by a lot of people, actually just straight up a lot of people use it. So these are two kind of baseline maintained branches. But again, you don't really have to worry about this too much. And if you go on Bridges and look, we've got a lot of variations of these just because some people have a preference for one or the other. And you can feel free to experiment. Load different modules. We're automatically loading the OpenMPI 4.05 module with the NVIDIA compiler for this workshop. Go ahead and load the Intel compiler with MVA pitch and try it on your examples if you want. Very easy to do. The standard has kept very core philosophy of saying we're not going to add things in here that we can't actually expect everybody to implement. So there's a lot of nifty stuff they're tempted to add, like interrupt driven receives, where the message comes in and automatically triggers some code. But a lot of hardware just can't automatically execute that. So it's similar to active messages. So that they don't roll stuff into the standard unless hardware can all support it. And that's wonderful for you as a code writer. You don't have to worry about portability issues at all. So they don't do things just for the sake of doing the latest shiny. So some of the things that are kind of on the borderline of what they can do, fault tolerance. Fault tolerance is a very, very difficult problem to solve. It's an important one when you build a machine with 1 million processors, because even if a processor is reliable for 2 or 3 years at a time, when you got 1 million of them at one place, things are going down constantly. So having a machine that's fault tolerant is super desirable, but it's an extremely difficult, it's essentially an unsolved problem as to how to deal with fault tolerance at large scale. MPI has at least started to define better how things will fail, but MPI won't buy you fault tolerance. It just assumes that things will work correctly, but at least it reports when things break a little bit better, but they don't solve problems that can't be solved. Remote memory access, well, you've seen the latest stuff that's going on there. Hybrid programming, as I said, there's lots of other different approaches out there for doing parallel programming. We're going to talk about, well, all of these in the outro talk in a little bit, but they all work well with MPI because they get better. Let's see, Fortran 90. There's the things have continued to improve well since Fortran 90. The Fortran 2008 standard has brought along some automatic type checking. So many of you working in a Laplace code accidentally are using the wrong types and find out the hard way that something should be a float instead of an int. So there's better type checking. The array subsections that we talked about are supported well. The error code stuck on the end of things is now optional. So there's a lot of nifty stuff if you use the module, the Fortran 2008 module, instead of the classic MPIF header file. So if you do the use to MPI 2008, you'll find that it brings along some nifty stuff as well. So which features to use of all the many routines in the MPI library? As I said, you're going to be fine if you start out using blocking sends and receives and build your code and get it working, and then try to optimize your way from there. You're not going to regret that you didn't, start with at some higher level. You're not going to be sorry. So don't feel anxious. You need to use the fanciest stuff right up front. As you get more advanced, and as you start to write codes, I hope at least a few of you want to use these new exascale machines or existing machines that have 100,000 plus or 1 million plus processors, in which case you do start to pay some more attention to doing things in the most optimal way as your code scales. And I hope you've seen that MPI is perfectly happy to accompany you on that journey, but you're not going to regret that you wrote yourself into a corner if you don't start out, at the highest level of optimization. So don't be intimidated by all the stuff. I hope you're now aware of all the things that are out there, but grab the pieces as they're useful to you and make your life better. Don't be compelled to just use them because they're slightly more optimal. Okay, the last thing we'll do here is a little advanced quiz here, pop quiz, and maybe we'll talk about this at the end of the day here, so I won't give away the answer just yet. But if you want to take a look at this exercise, I'll leave it up for a little bit. We're heading into our lunch break right now. So here is something that's a little, I'll say tricky, but it's not tricky. If you understand now how collectives work, and you should be able to figure out what the correct answer to this question is here. So we've got a bunch of processors here. We've got 8 processors, and the even ones are going to participate in this section of code, and the odd ones are going to participate in this section of code right here. So what is the end result going to be for the reduced sums that they're going to come up with here by reducing their P numbers?